Hello, everyone. Today, to make an introduction for our second committee experiment, I prepare a short video for you. Before coming the laboratory, please watch this video. So, our second committee's experiment is first law of thermodynamics, and our purpose in this experiment verify this law. So it's actually conservation of energy. To do this, we will measure temperature of aluminum body as a function of number of rotations against the friction course, and then we will investigate proportionality between the temperature change and the frictional work, and we will thereby verify the first law of thermodynamics. We will also determine the specific heat of aluminum. So first law of thermodynamics says us the change in internal energy of a system, which is delta E, equal to the sum of work performed on the system, which is delta W, and then the transferred heat. This transferred heat, let's assume that it's delta Q. So delta E equal to summation of delta W and delta Q. Internal energy can be measured as the proportional change in the temperature of system delta T, and then assuming no change in the state of aggregation and that no chemical reaction occurs, we will assume that we will investigate this relationship by by performing the experiment in the experimental setup that you see on the left side. We have an aluminum cylinder connected to a bucket, and the cylindrical body rotated about its axis. We will have a crank to operate this system. As a frictional cord runs over the surface of cylindrical body, aluminum cylindrical body, it will provide us a friction. And then the cord, you see here connected to a bucket as well as counterweight that balance our friction force. And this is our experimental setup. This is our crank. We will rotate this crank. We have a water-filled bucket, and we have a cord, as you see here. So this is our experimental setup like that. So the experiment is performed in the video that I will also add our channel, and we do not directly measure the temperature. Instead of, we will measure the resistance, as the resistor inside the cylinder is temperature sensitive. So resistance is temperature sensitive. For our system, we have a specific equation. You can see on the apparatus how we can obtain this equation actually. So for our measurement system, we have a resistance dependent equation. So according to measured resistance, we can calculate the temperature. So during the measurement, part is the rotated cylinder using the crank. You should have been careful. Bucket is not moving up during this process, so we won't move the buckets. So we will measure resistance, and we will stop 25 rotation and note the resistance that we see on the digital multimeter. And when we reach 300 rotation, we will finish the experiment. Okay, so this is our table. Sorry. N is number of rotations, R is the measured resistance, and T is the value that we calculate for our system. We have a specific equation for this system. Now I want to explain you the other details for the calculations. So we have delta W. Delta W is the work done on the system. We have delta E. Delta E is total energy of the system. And then for the work done here, if we calculate the work done here, as you know from your high school information, the work is equal to force times displacement. So F times S. So F here for this system, it equal to mg. What about displacement? Okay, we have a cylindrical part here. For this cylinder, diameter is 2r, which is equal to diameter cylinder decile. So here, number of rotations times pi times d cylinder, so which is 2r, will give you the displacement. These are the known things for our system to calculate the work. So m, mass of the bucket, g is gravity, gravitational acceleration, n is number of rotations. You know what is pi, and the decile here is 2r, which is diameter. So we know all of the things here, so we can calculate work done on the system. For example, if you calculate for 25 rotation, you can find if after inserting all of these things there. If you increase the number of rotations up to 300, for every rotation number, you can calculate the work done on the system. So let's look at the other thing. We can calculate the internal energy, which is affected by the temperature, you know. So if you calculate, we know the temperature. If you calculate the internal energy here, it will be equal to mc delta T. So mc delta T. M is M aluminum, C is specific heat of the aluminum, and delta T is final value of the temperature and then the initial value. So we will assume that from with the environment, there is no external heat added to our experimental setup. Because of this, no additional heat will be in the system. We will assume that. So delta Q equal to 0. If delta Q equal to 0, delta E will be equal to delta W. So the energy, internal energy of the system will be equal to the work done by the system. So here, if you make the equation, so mc delta T equal to the work done on the system. If you write here Tn, so final temperature value, you can rearrange the equation like that. So after arranging this equation like that, this will give you a mathematical equation similar to y equals c plus mx. So m is here slope, okay? So y and x, you know, what are these? So from here, m is slope. So if I draw a graph that contains work done on the system and the temperature, and we know this, we found this from the system, I can find this slope value, okay? So if I make a graph that I obtained by using the experimental values, so temperature values calculated, we know that, and then we know the work done on the system, I can plot a graph and I can find slope of this graph. So the mass of the aluminum body is known. We will give you this which is 250 gram. So after calculating the slope of the system, slope of the graph, and making this equalization, which is known here, so m is 1 divided by m aluminum times c aluminum, and I know what is this slope here. If slope is equal to 1 divided by m aluminum times c aluminum, I can find the specific heat of the aluminum from this equation, and C aluminum will be equal to 0.91 joule per gram Celsius degree. So this is the value that I found from my experiment. If I calculate with this known literature value, which is 0.90, I can calculate the error percentage here by using this system. So my assumption here is that to find the specific heat internal energy of the system at the end is equal to work done on the system, and we will correct the first law of thermodynamics with this experiment. Please watch this before coming to the laboratory.